This is my friend Amir, and he is about to jump off a waterfall. Now, at the time, we didn't really have a rope or anything that I brought. Heck, I actually forgot to bring a towel. But I would like to know how high the waterfall actually is. Like, I'm not sure. I wonder if there's like a mathematical equation that we can use to find this.
Actually, there is. To find out the height of a waterfall, we can use the kinematic equation that goes as follows. S equals to V initial multiplied by time plus half acceleration times time squared. Now, don't be scared. I know it might seem a little complicated, but I will break it down for you. To calculate the displacement of a moving object, we have to take into account how fast it's going and how long it's going that fast. This explains the first half of this equation. Since we're talking about free fall, we need to take into account the acceleration of gravity. This is what the second half of the equation is for. Half times acceleration multiplied by time squared. Now that we've understood this equation, we can simplify it. Since Hazik's friend didn't get pushed down the waterfall, the initial velocity is assumed to be 0. This gets rid of the first half of this equation. We also know that the acceleration due to gravity is 9.80 meters per second squared. Now, if we halve that following the equation, we get the final simplified formula to be S equals to 4.9 t squared. So in theory, we can use this formula to calculate the height of anything on Earth based on the time it takes for an object to fall from that height.
Thanks, Lukman. So now I want to just further prove that his equation makes sense by doing dimensional analysis on this. So his equation is the height, which we'll label as S, equals the initial velocity, we label as U, times the time plus half of the acceleration of gravity times the time squared. As he explained, the height is how fast you're going and how long you're going that fast, and the factor of how fast gravity is accelerating you to the ground. So we know that the dimension of S is in meters, because we are not America. So that is the dimension of length. And then the dimension of U is velocity, which is meters per second, which is length over time. And then obviously T is equal to time. And then A, which is the acceleration of gravity in this case, because free fall is going down, is length over time squared. So now we got all the dimensions down. Let's just see if the dimension of S, which is L, is equal to this equation over here. U is L over T. T is, well, T. Plus 1 over 2 is a dimensionless constant, so we don't need to write that. A is L over T squared times T squared. So this cuts, this cuts, this cuts, this cuts, and just with basic algebra, you can see that is dimensionally correct. And therefore, that means Lukman's equation is correct.
Yeah, but how do we know that this guy's equation is actually correct? Like, look at this guy. Does he really know what he's actually saying? So, to prove his equation, we will conduct an experiment.
This guy. So, we started off by releasing a ball off the first floor and measured the time it took for it to hit the ground. 0.84 seconds. We then repeated the experiment 2 more times to ensure we get the most accurate results. 0.81 seconds. So, editor Hazik here. Basically, while editing this, I realized since we recorded the balls dropping on video, we could just use the frame rate, which is 30 FPS, and count the frames in between when the ball is released and when it hits the ground. And from that, we can determine precisely the amount of seconds it took for it to hit the ground. So this will give us a more accurate result. So yeah, now back.
But there's one thing that Hazik forgot to mention. We are using a ball who has high surface area. This will make a lot of air resistance affecting upon the ball, which will raise the question, will this affect the time taken for the ball to reach the floor? That's one of the good questions. Scientifically, it affected very little. Like, it's negligible, you can ignore it. So, to test this out, we use a stone. This stone, as you can see, it has obviously lower surface area than the ball. So as we drop it, you will notice that the time taken is about the same. But there's one question that you might ask yourself. Isn't the mass of both objects different? Will this make the difference?
So, mass actually has no effect on the time taken for an object experiencing free fall to hit the ground. Now, at first this might seem counterintuitive because if I drop a leaf and a rock at the same time, the rock hits the ground first. This can actually be explained by air resistance. The only thing that makes them have a difference in time for hitting the ground is air resistance. So, theoretically, in an environment with no air, both the leaf and the rock will hit the ground at the same time. This is proven by astronauts that dropped a hammer and a feather on the moon's surface, and both of them were found to hit the ground at the exact same time. We then measured the actual height of the drop using a rope and some measuring tape we stole from an AEDU student. To make sure air resistance didn't affect our results as much, we started using a stone and also repeated that 3 times. And another 3 times with the ball on the second floor, and just before the sun goes down, another 3 times with the stone.
So now that we have conducted the experiment, we have enough data for us to make the use of the equation that Lokman has given. So this is the time taken for the ball and the stone to hit the ground for the first floor. As you can see, we have recorded 3 separate times for each experiment we conduct. It is crucial for us to make sure the value is as precise as possible. That's why we have 3 separate values right here. So in order to find the average, we just need to sum up these 3 values, which is 0.83 plus with 0.80 plus 0.80 divided by 3. We get the value of 0.81 seconds. Now we just need to plug in the value into the equation to find the height. S equals to the initial velocity, which in this case the value is 0, and times with t, which of course 0 times anything will be 0, plus with half of the acceleration. In this case it is 9.8 times with the value we get, 0.81 seconds squared. We put this into the calculator and we get the value of 3.21 meter, which is nearly the same as the height we took at the time. So now we just can do the same for the stone. We get 3.37 meter, which is nearly the same. So now we go to the second floor. Same as before, at first we need to find the average for the time of the ball, and for the stone to find the height, S equal to ut plus 1 over 2 at square, the equation we use, and so we get the value of 6.82, and for the stone we get the value of 6.15 meters. So as you can see, this equation does work to find the height.
So, now that we know this equation works, we can use little stones and be able to estimate the height of any building in CFS. So let's go and do that. Why not?
2, 1.
Why did it have to fall in the drain? It fell in the drain. Oh god.
So after asking some volleyball players awkwardly if they could send a ball up in the air, we were able to measure how high it went. And that turned out to be 9 meters.
So, one thing we kind of forgot to do is to actually measure the height of the waterfall using the time taken for Amir to jump from the top. We can use the frame rate and how many frames it took for him to get from the top to the bottom, and then we can find out how many seconds it took, and from that we can conclude that the waterfall is about estimated to be 3 meters high.
I hope you can use this equation in your daily life if you ever want to jump off a cliff.
If you want to watch another video about kinematic equations or any other physics videos, you can click here or down in the description below.
Thank you for watching.
Bye!